So on page 468, you have some space on the side there. We are going to review some concepts, and the first concept, oops, that's not a highlighter. The first concept that we are going to review is an angle in standard position. So, don't have to write this down, but for now, I'm going to draw an angle here. Let's say this is 40 degrees. Is that angle in standard position? No. Okay, that is correct. So we'll write no here. And over here, we'll do an example of one that is. There's an example of one that is in standard position. I'm going to draw another angle here. You have to tell me, very fun game, yes, no. Is this angle in standard position, yes or no? The answer to that one is yes, it is. So that's an example of one that is in standard position. Make it a little smaller. Oops, there we go. Keep it over here. Draw another one. Yes or no? No, that is correct. This one is a no. We'll put it over here. Is this angle in standard position? Yes. So off to the side, we're going to start and we're going to put a definition. An angle is in standard position if. Now we got to look back here. If what? How do we describe the difference between the yes ones and the no ones? How do we describe the definition of something being in standard position? Okay, all of the ones on the yes side started from that one side. That is true. So we can go to our definition here. An angle is in standard position if it starts, how are we going to describe that one side? On the positive x-axis. Does that make sense for that side? Can't start on the negative x-axis. Has to start on the positive x-axis. So any angle in standard position has to start, and all of these ones started here. Okay? I should have probably drawn, so here, if I draw this angle and have it end at the positive x-axis, that angle is not in standard position. It has to start on the positive x-axis. Anytime that you have an angle in standard position, it will be a positive angle if you're going counterclockwise. That means starting here, going this way. All of those angles will be considered positive. And your angle will be in standard position but negative if it's going clockwise. So again, starting here but going this way, all of those will be negative angles in standard position. That's definition number one. That's going to be really important. And the reason we have angles in standard position and why we standardize things and have definitions like this is so if someone is talking about an angle of 80 degrees and they tell you it's in standard position, you can understand exactly which angle they're talking about. So it's a way of communicating things so that everybody understands the same thing. Our next thing that we're going to look at is reference angles. So if I took an angle of 150 degrees, what would the reference angle be? 30 degrees. This angle right here would be 30 degrees, and that would be the reference angle. How did you find out that that was 30? So you have 180, you could subtract the 150 and find that that's 30 degrees. What about if we went here and said this was 200 degrees? What would the reference angle be? 20. So again, the reference angle is right here. It's not this part right here. And if I do one more example, let's go all the way around and a little bit more. Let's say this is 400 degrees. What would my reference angle be? My reference angle, we often write it with theta with a little r. My reference angle would be 40 degrees. How did you figure that one out? Well, this part right here, all the way around is 360. So to go 400, we'd go 360 plus 40 more. How do we write a definition for this? What is a reference angle?
The distance away from the x-axis.
Okay. A reference angle is the angle to the nearest x-axis. It is always positive and always between 0 and 90 degrees. Always positive, always between 0 and 90 degrees, and including 0 and 90 degrees. So, for example, if I were to draw a standard angle starting here of 180 degrees, the reference angle would be 0. If I started with a standard angle of negative 90 degrees, well, what's the nearest x-axis? They're both equally the same, but you're still 90 degrees away. I think where students are most tempted to make a mistake, standard angle, let's say this is 260 degrees. I think this is the one that's most tempting to make a mistake because you're like, oh, it's only how much further do you have to go to get to that? And then you go to the y-axis, right? Yes, it's only 10 degrees away from the y-axis, but your reference angle is here back to the x-axis. So it would be positive 80 degrees. So we have standard angles so that we're all talking about the same thing. Why do we have reference angles? What are they useful for? Well, I'm going to check some of your memory here. I'm going to check. I'm going to write an angle of 30 degrees. If that angle is 30 degrees, your reference angle is also 30 degrees. And this was one of the ones in grade 11 that you memorized. So let's see how much your memory is holding. Do you remember what sine of 30 degrees is? Close. Sine of 30 degrees? One half. So some of you might remember it when you see it. Some of you might not even remember that you learned it. That's fine. We're going to relearn and memorize all of these ones that we can do without our calculator again this year. But sine of 30 degrees is 1/2. Now, what is your definition of sine? Definition of sine is opposite over hypotenuse. So if we made a triangle, straight down here, made a right angle triangle, that would say if I measured this side and it happened to be 2, then the hypotenuse here would have to be 4 because my opposite over hypotenuse has to equal a half. In this case, is 1/2 the same as 2 over 4? Yes, it is. I could measure it somewhere else. If I measured it here to be 1, this side would be 2. And that ratio, no matter how big or how small you make that triangle, will always be that. Now, I was going to say, what is the reason for a reference angle? Well, a reference angle is important because if I go to quadrant 2 and I get a reference angle of 30 degrees, so here's my reference angle of 30 degrees, what's my angle in standard position? 150. And sine of 150 degrees is also 1/2. Because if you make a right angled triangle, it's the same triangle. The opposite over the hypotenuse will still be 1/2. And because we have the triangle with the 30 degrees, sine of 150 is the same as sine of 30. Now when we go to quadrant 3, there's a small change. So if I draw a 30-degree reference angle in quadrant 3, meaning that my angle in standard position would be 210 degrees. And if I draw a triangle, that's going to be the same triangle that we had before. So sine of 210 degrees is also 1/2, but if you type it into your calculator tells you -1/2. And same thing if we did the reference angle of 30 degrees for quadrant 4, looking at 330 degrees. Type that into your calculator. We also get -1/2. Now, why are these ones negative? Well, last year you might have learned the cast rule that tells you where things are positive. They're all positive in quadrant 1. In quadrant 2, sine is the only one that's positive. That's why sine of 150 was 1/2. And in quadrant 3, only tan is positive, so sine would be negative, -1/2. And in quadrant 4, only cosine is positive, so sine would be negative again, and we get -1/2. That's one of the things that you would have learned. The reason why that happens is sine is opposite over hypotenuse. Now, for the mathematics, when solving for the hypotenuse, in all of these, the hypotenuse stays positive. The opposite side is your y in this case. Can you see in quadrant 1 that your y is going up? It's a positive number. In quadrant 2, it's going up. It's a positive number. But when you get to quadrant 3 and quadrant 4, your y values are negative, and so that is one of the reasons why sine appears negative in quadrant 3 and quadrant 4. Now, the powerful thing about reference angles is if you know sine of 30 degrees is 1/2, you now can do 150, 210, 330, 390. You can keep going around over and over again. And as long as that reference angle is 30 degrees, you can figure out what sine is. So that's the power of the reference angle. If you can figure out the reference angles, then you can figure out the other angle. And the last definition that we're going to add on this page is a coterminal angle. All right, so if I have an angle of 5 degrees, can you tell me a coterminal angle? $85. So if we have 85, 85 plus 5 adds up to 90. And any two angles that add up to 90 are called, starts also with CO, but not coterminal. They're called complementary. And angles that add up to 180 are called supplementary, but those ones aren't coterminal. The hint for coterminal is in the word itself. An angle that's coterminal with 5 degrees would be 365 degrees. That one would be coterminal with 5 degrees, or negative 355 degrees. The hint is in the word. On an angle, the terminal arm is where the angle ends. A coterminal angle is an angle that ends in the same place, because they share, in English, when you have a word that starts with co, like cooperative, co-ed, coexist, things that share something. So they share the same terminal side. So if we add to our definition, a coterminal angle is an angle that shares the same terminal arm, aka it ends in the same place. So as a final example for coterminal angles is if I make up an angle of, let's say, 20 degrees. What's a coterminal angle with 20 degrees? Sorry? 380 is one. Can you tell me another one? Negative 340. Good. That's our first positive one and our first negative one. I guess technically we could also say 20 degrees, because 20 degrees ends in the same place as 20 degrees, but that's really obvious. How about another one? $740 degrees. Another one. Negative 700. How could you keep on going forever? Well, yes, but any larger number works? We have to keep adding or subtracting 360 degrees, right? And we could list them all. And you're going to sometimes be asked that. What are all the coterminal angles with 20 degrees? Listing them is going to be a problem. Because if we have to write them all, and there's an infinite amount, it's going to take forever. And they're not going to, but they will ask you that question. But if you try to write them all out, you'll be there forever, and you won't get done. Because there's an infinite amount of them. So how are we going to do that? Well, sometimes people say, well, let's just start listing them. Here's 20 degrees, and then 380, and then 740, and then maybe make some dots so that someone can follow and say keep on going. And then we'd have to go backwards as well, right? Negative 340 and negative 700, and keep on going as well that way. That might be one way to try and show that it keeps on going and has a pattern. The way that mathematicians would like to write them all down is they say, Well, what is the pattern that you see? The pattern that you see is you're adding 360 or subtracting 360 as many times or as few times as you would like. So how do we write that? Well, all the coterminal angles with 20 degrees would be written this way. Start with your 20 degrees, then add 360 degrees times by k. And k can be any positive number, like 1, 2, 3, 4, 5, 6. It can be any negative number, negative 1, negative 2, negative 3, negative 4. Because we could, if we have a negative number, then we would be subtracting. Or it could be 0. And if k is 0, that would mean that we have 20 degrees. So what are those numbers called that I just described for k? 1, 2, 3, 4, 0, negative 1, negative 2, negative 3. They're not real numbers, because real numbers would include 1.5. And real numbers would include 2/3. But we're just looking at 1, 2, 3, and negative 1, negative 2, negative 3, and 0. Whole numbers would just include the positive ones. So our whole numbers would be 1, 2, 3, 4, 5, 6, and 0. But it wouldn't include the negative ones, integers. So we need to say, after we write this, we need to say that k is an integer. So if I write that in words, we would say where k is an integer. Now, mathematicians tend to not be English majors, and they tend to not like to write a lot of stuff. So whenever they have to write a lot of stuff to describe something, they come up with symbols to write it shorter. 20 degrees plus 360 degrees times k, and I want to write where k is an integer in a very short way. The way that we would do that, k belongs to, and you know how you do XER to say all the real numbers? We're going to do the same thing, except we have to use the symbol for integers. Do you know what the symbol for integers is? In North America, sometimes they use an I. That is true. And if you have integers with an I, that's fine. Internationally, is more accepted to use the letter Z for integers. Comes from the German word for numbers, Zahlen. So that's saying all the coterminal angles will be 20 degrees, plus we can add or subtract 360 as many times as we want, as long as k is an integer. So this is how we'll write an infinite amount of things, instead of writing them all out by hand, which would take a long time. So the international symbol is the Z, yes.